Hello, this is Miss Moore, and today during chemistry, we're going to discuss double replacement reactions and solubility. So today's essential question: how are the solubility rules used to determine if an ionic compound will form? So we've already discussed or learned how to predict products for double replacement reactions. But today we are going to apply the solubility rules to see if a product actually occurs. So let's get started. Many reactions, displacement reactions, single or double replacement reactions or displacement reactions occur or happen in solution. What does that mean? Well, reactions in solution, what that means is that the ionic compounds are dissolved in some solvent, usually water, which means that ionic compounds are aqueous or AQ. They're not bonded together. They're just the two ions of positive and negative are just floating around. So for example, we could have the reaction AlBr, or aluminum bromide, plus Na2S, or sodium sulfide. But it turns out, sorry, that's kind of messy, that these ionic compounds are in the aqueous state during this reaction, meaning that they're dissolved in water. So even though we're still writing them as AlBr3, they are really separated into their cation and anion components. So they're just floating around like they're, right? Floating around separately in this water solution. That's what we mean by aqueous. So if we take this reaction here, AlBr2 plus Na2S, we'll still predict products like we've been practicing, but now there may or may not be a reaction. If there is an actual reaction occurring, a precipitate will form. So what do we mean by precipitate? A precipitate is a solid that is formed from ions forming bonds and coming out of solution. I'm going to jump ahead to the insoluble first. Something insoluble is something that does not dissolve. It will form a solid, a liquid, or a gas. That's what we mean by a precipitate. Okay, so a solid, a liquid, or a gas. Versus something that is soluble, that is something that's going to dissolve in solution, like our original reactants up here, AQ. So something that's soluble is aqueous, and we abbreviate that AQ. So when we're predicting product for double replacement reactions, to determine if an ionic compound will be soluble or insoluble, or if it'll actually form an ionic compound, we're going to be looking at our solubility rules. So a reaction will occur if we form a solid, meaning something that is insoluble, or if water, which is a liquid, is formed. The solid or the water is the actual product. If both products are aqueous, That means there was no reaction, or NR. Right. So now we're going to try a couple different practice problems. Please work through both of them with me because you'll be learning something different with each one. All right, so first practice problem. Let's get past that for now. We'll have that there. All right, well, let's do the one I had written before. We're going to have aluminum bromide, which is aqueous, plus sodium sulfide, also aqueous, and from here we're going to predict our products. Now, the first part of this is stuff we've already done. We figure out the charges, so hopefully we know that aluminum, which is right here, is going to have a 3+ charge. Let's see, bromine is going to have a 1- charge. Sodium, 1+ charge, and sulfur, 2- charge. Okay, just like the double replacement reactions we've been practicing, the two metals switch places, and we do not bring our subscripts over to the reactant or product side, sorry. So we're going to have Na. Let's keep the colors the same. All right, so we're going to have Na 1+, now hooked up with Br 1-, and I didn't leave myself enough room. Oh, I put the parentheses here so that we can look up the state of matter, solid, liquid, aqueous, whatever, later. Plus, let's see, our aluminum 3+ is now going to hook up with our sulfur 2-. All right, so far so good, hopefully. We now need to make sure that our charges are all neutral on our ionic compound, so we know that this side's good. If we look at the NABR, we have a 1+ and a 1-, so those are neutral. And then we have our Al2S. We have a 3+ and a 2-. Those are not neutral. So let's see, we need 2 aluminums and 3 sulfurs. That will neutralize those charges. Get rid of this. Okay, now the new part. Before we balance the reaction, we need to look up and see if either or both of these products were produced. So we'll start with NABR. We're going to find bromine on the solubility rule chart and then look and see if when it's hooked up with sodium, if it's soluble or insoluble. Okay, bromine is a halogen, and most are soluble, meaning AQ, except when bonded with silver, lead, or mercury, but ours is hooked up with sodium, which means our NABR is aqueous. All right, and next we're going to check aluminum hooked up with sulfide. So we'll find sulfide here. Most are insoluble, meaning a solid, except when bonded with ammonium or group 1A or 2A metals. Aluminum is a 3A metal, which means aluminum sulfide is going to be a solid. Okay. That means we have made an actual product. We actually made this. Okay. And the NABR is still in the aqueous state. So our very last step is to balance this guy. So let's do that real quick. Let's see. We have, I didn't leave myself a ton of room here. Aluminum, bromine, sodium, and sulfur. On the reactant side, hopefully I'm doing this right. We have 1, 3, 2, 1. And on the product side, we have 2 aluminum, 1 bromine, 1 sodium, and 3 sulfurs. So let's see if I put a 2 here. This will give us 2 and 6. Bromines, let's see. I guess I could put a 6 right here, giving us 6 and 6. Let's see, got to fix our sulfurs. 6 and 3, and I think we're good. All right, so the new part of this was, again, checking the solubility rules and finding out that we actually made aluminum sulfide. All right, let's try one more. Please, please don't quit yet. Let's try this next one with me, okay? So this time we're going to take H2SO4, or hydrogen sulfate, which is an aqueous, plus NaOH, which is sodium hydroxide, also aqueous. And let's mix those up, see what happens. So we'll check our charges. Let's see. We have a 1 plus for hydrogen, a 2 minus for sulfate, 1 plus for sodium, and a 1 minus for hydroxide. And again, our positives will be our metals. In this case, our positive will be swapping places. So, sodium, 1 plus, is now going to hook up with, and then again, SO4, 2 minus, and hydrogen is going to hook up with OH, 1 minus. Okay, so far so good, I hope. Next thing we're going to do is check to see if our charges are neutral. So NaSO4, we have a 1 plus and a 2 minus, not neutral. So let us add 2 NAs there, right? So Na2SO4 is now neutral. And next we have the HOH. So this is where we need to think. So first of all, the neutral, not neutral thing. 1 plus, 1 minus, they're neutral, so we're good there. But what I'd like you to notice is that we have 2 H's here and an oxygen, right? 2 H's and an oxygen. That is actually H2O. 2 H's and an oxygen. Okay, so whenever you have HOH as an answer, that's actually H2O. Okay, so what we did there is we made water. And I forgot to leave space for my states of matter. All right, so the solubility rules for us, these are all going to be solids, okay, except one thing, and it's not on your solubility rules. HOH, which makes water. Water is a liquid. Water is not aqueous. Aqueous means dissolved in water. Okay, water isn't dissolved in water. Water is water. Okay, so when you see H2O, which remember was HOH, that's a liquid. Okay, so we don't even have to look that one up. We do, however, need to look up sodium sulfate. So we're going to find sulfate, 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 sulfate. Okay, most are soluble, meaning AQ, unless except when bonded with calcium, strontium, barium, lead, or mercury. Ours was hooked up with sodium, so we are aqueous here. Okay. Yeah, there you go. So did we make an actual product? We did. Our actual product here is our water. Okay. And then our very last step is to balance. Let's see, we have H. SO4 we can keep together because it's on both sides. We have Na. We cannot keep our OHs together because they're not on both sides. So we have an O. All right, so our H's, we have 2 and 1. So 3 and 1 SO4 and 1 Na and 1 O. On the product side, 2 NAs, 1 SO4, 2 H's, and an O. All right, we are going to save. Nope, not that one. We're going to save the H's till last for balancing because they're split up here and here. That'll hopefully make it a little bit easier. We'll see. Okay, so moving on. SO4s look good. NAs not so good. If I put a 2 here, I now have 2 NAs, 2 O's, and H's. I have 2 plus a 2 over there, which makes 4 H's, right? So I have the 2 and then those 2. All right. So where am I at? I just lost myself. So I need to fix the O's. So I'm going to put a 2 here. Try that again. Put a 2 here. That gives me 4 H's. Yay! 2 O's. So there you go. So remember, for a reaction to occur, a double replacement, if the reaction occurs, we've made a product. That means one of your products okay, let me rewrite this. If a reaction occurs, at least one product must be a solid. Remember, that means insoluble. Or water. No reaction means both products are aqueous, AQ, which means soluble. Okay. All right, guys, that's it for today. Have a good one.